There you go, start recording there. I'd like to welcome everybody to the Texas Water Journal webinar series. This is the third webinar that we have put together, and we're hoping to have more webinars as we go on. Certain articles produced by the Water Journal are conducive to having a webinar, and today is one of those examples. So just a few things about the Water Journal before we get started. First of all, the Water Journal is peer-reviewed publication that's published by the Texas Water Journal 501c3 and the Texas Water Resources Institute at Texas A&M. Our first issue was published in 2010. We publish articles as they're ready. Everything is online. And the journal is free. We've got a whole bunch of folks who are working to bring you the journal. I invite you to go to our website, texaswaterjournal.org, and take a look at everybody who's contributing. And just a couple of more items here. We have 4 types of articles in the journal. First of all, our general research issues. Then we've got research policy program or legal reviews, book reviews, and then commentaries. As for our webinars, we're charging a fee which supports the journal's out-of-pocket costs. For example, Zoom webinar. I certainly appreciate everybody contributing today because we'll be able to pay for Zoom webinar for 4 months based on the folks who signed up today. And we certainly do appreciate that. Coming up in the future for our webinars, we're hoping to be able to offer CLE credits. So today, the article that is inspiring our webinar is called Exploring Groundwater Recoverability in Texas, Maximum Economically Recoverable Storage. The authors are Justin C. Thompson, Charles W. Kreitler, and Michael H. Young. And so with that, I'm going to pass the baton to Michael, who is going to introduce today's speaker. Michael.
Great, thanks Todd, and welcome everybody, and thanks also for being here. Just as I was starting, we're getting a downpour outside, so which is amazing, right? It's hydrology in action. So it's a pleasure to introduce Justin Thompson to the Texas Water Journal webinar series. Justin is currently a PhD candidate in the Jackson School of Geosciences at UT Austin. He has a Master's of Science in Energy and Earth Resources and a dual Master's in Global Policy Studies from the LBJ School at UT. He has a very interesting background. Justin got a Bachelor's in Business Administration, International Business from Texas Tech. So he has a long-term family, many multi-generation Texan. He spent years as a senior analyst and investor relation officer for the Star of Texas Regional Center in Houston. He was manager of the Boulevard Utility Services in Port Boulevard, Texas. He spent 3 years in Wuhan, China before COVID, and was a senior foreign expert at the Wuhan Textile University. So he's been to the rodeo, as they say, even as a PhD student, and so it's a pleasure for me to introduce him. And Justin, take it away.
Just one note before you start, Justin. As Justin goes along and you have questions, please go ahead and submit them. You can see the Q&A button down there, and when we get to the end, I will go through those and ask a representative group of questions to Justin.
All right, well, good morning. Thank you all for being here. Thank you for that introduction, Dr. Young. As we said, so today I'm going to talk to you all about exploring groundwater recoverability in Texas. So the question at hand is how much of stored Texas groundwater is recoverable? I once heard it said that the simplest questions are the hardest to answer, but I think with this one, we can make some progress. So let's start just by talking about what is recoverability. Well, here we're talking about the relative ease or difficulty of human extraction, right? We define that in our paper as dollars per volume. So dollars per gallon, dollars per acre feet, something along those lines. It's one key element of availability and yields. And generally speaking, again, for our purposes here, it's constrained by the aquifer, well, and economics. So our key questions are, how could recoverability be numerically defined and simulated? And how might changes in recoverability impact Texas' most sensitive users? Our principal hypotheses are that in shallow and unconfined settings, physical constraints, not economic ones, limit recoverability. And in deep confined settings, the opposite is true. Economic constraints, not physical ones, will limit recoverability. So first, let's talk about motivation. Why does this study matter? Well, first, let's talk about the State Water Plan, 2017 Water for Texas. The plan projects that under drought of record conditions, Texas will experience water deficits of 8.9 million acre feet by 2070. It also projects a 70% increase in the population by 2070, concurrent with an 11% decline in total water supply. Now, what's interesting about that decline is that surface water supplies are projected to remain relatively flat, a modest decline here and there. So 95% of the supply declines that are projected are actually from groundwater availability. Let's look at groundwater availability a little bit here. This chart here is from the Texas State Water Plan, and it shows groundwater availability in orange and water supply in blue. The difference between supply and availability is essentially that supply is connected to existing user groups. And what I want to note here is that the Ogallala is far and away the number one in terms of availability, and then the Gulf Coast aquifer, and then the Carrizo Wilcox, and then the remainder of the state aquifers sort of drop off rather quickly from there. I want you to kind of keep this in mind as we go along, and we'll see why that's interesting. Now let's get into what I like to call the alphabet soup of groundwater management in Texas. Some folks in the audience are very familiar with this stuff, but others might not be. So let's just put a little primer here. First, we have groundwater conservation districts, or GCDs. These are the primary Texas groundwater regulatory entities. They range in size. Some of them are the size of a county or a sub-county, and some can be quite a few counties all lumped together. Then we have groundwater management areas, or GMAs. These are generally composed of a group of GCDs within an aquifer footprint. Then we have desired future conditions, or DFCs. What do we want the aquifer to look like over time? Now, there's a whole range of desired future conditions that we see across the state, everything from saturated thickness metrics to spring flows. But what is most commonly the DFC across the state is some form of depth to water change. Then we have the Texas Water Development Board, or TWDB, and they produce a couple of things. They produce a groundwater availability model, which is a scientific model of the aquifer characteristics and the flow of water within the aquifer. And then they also produce something called modeled available groundwater, or a MAG, and we'll come back to that and explain what that is in just a second. For clarity and specificity, GCDs are obligated under Texas law to meet their desired future conditions. That's their management goal that they're trying to meet. For planning purposes, groundwater availability in the state is equivalent to that modeled available groundwater. So what does that all mean? How does this all work together? Well, let's illustrate visually real quick. So first, we have a group of GCDs within a groundwater management area, and they collectively come together to adopt a desired future condition. For example, our DFC is 25 feet of drawdown over 50 years, right? So a change in depth to water over time. That DFC then goes to the Texas Water Development Board, who sort of combine it with the groundwater availability model to come up with that modeled available groundwater number. So that's essentially the volume of producible water under that DFC, whatever it might be. So for example, our DFC is 25 feet of drawdown over 50 years. Okay, then you have 100,000 acre feet to allocate annually, for example. How do those DFCs get determined? What goes into that decision-making process? Well, the Texas Water Code lists quite a few considerations for DFC adoption. The first one, things like feasibility of achieving that desired future condition, aquifer uses or conditions, water supply needs, to environmental impacts like spring flows, as we see pictured here on the right. Subsidence, right? Land surface subsidence under groundwater production. And then a few pieces that we're particularly interested in here, like socioeconomic impacts, the interest in rights and private property, and hydrological conditions. Now, hydrological conditions include things like recharge, the amount of water that's flowing into the aquifer, discharge, the amount of water that's flowing out of it, but also this interesting term called total estimated recoverable storage. Let's look at that term a little bit. Total estimated recoverable storage was established by Senate Bill 660 of 2011. It is essentially currently Texas's best estimate of groundwater recoverability. It is 25% and 75% of total aquifer storage. When we look at this total storage term, and there's a table published in the paper you can look at for all of the major aquifers in the state, we see some interesting things. We see quite a lot of storage, actually. The Ogallala has about 380 million acre feet stored in it. The Gulf Coast Aquifer has over 4 billion acre feet in it, and the Carrizo-Wilcox stores over 5 billion acre feet. So TERS being two numbers, for example, 25% TERS for Carrizo-Wilcox is about 1.3 billion acre feet, and TERS 75% of Carrizo-Wilcox is about 3.9 billion acre feet. So let's look over here to the right and see kind of how that number gets calculated. This is a graphic that I've pulled from the TWDB TERS reports, which kind of illustrates this process. On the left, what we see is an unconfined setting aquifer. And essentially, total storage imagines, well, what would happen, how much volume would be produced if we drained this aquifer completely, if we took the current water level and brought it all the way down to the bottom of the aquifer. You calculate that number essentially by just multiplying the area that you're interested in, acres or square miles, whatever it might be, by the depth to water change. If you're talking about a total drain, then that would be the current water level to the bottom of the aquifer. And then you multiply that times the storage coefficient. And in the unconfined setting, that's a specific yield number, right? So for example, for the central Carrizo-Wilcox model, that might be about 0.15. On the other hand, in the confined setting, the calculation is just a little bit more complex. It's a two-step process. First, we consider the same storage number that we looked at in the unconfined setting from the drained pore space of the aquifer. But we also need to consider the pressurized storage of the aquifer, where the water levels exceed the top of the depth of the aquifer. Where that happens, where we're looking at confined storage, it's the same calculation, except the storage coefficient changes to storativity. And what's really important about that is storativity is much, much, much smaller than specific yield. Here, for example, specific yield 0.15 versus storativity 0.0003, right? So there's a really big difference in those two numbers, and we'll see kind of why that's important. These very large storage volumes reported throughout the state have led some folks to wonder, well, recalling the state water plan and that we're, projecting an 8.9 million acre feet deficit by 2070, but we have billions of acre feet in storage. Does that mean we're experiencing some kind of regulation-induced shortage? Well, I think maybe not, right? So first and foremost, remember that total storage is imagining we drain an aquifer completely. And we have to remember those DFC considerations that we looked at just a minute ago. There might be a number of reasons, subsidence, surface water flows, et cetera, why we wouldn't want to do that. But also, more importantly, we need to understand that the 25% and 75% metrics of TERS are essentially arbitrary limits. They're sort of a reference bracket. There's no accounting whatsoever of the limitations involved in pumping dynamics, nor the economic feasibility of withdrawing the water. So when we think about that, and we kind of recall this groundwater availability and supply numbers from that chart from the State Water Plan, and we saw what the Ogallala, which only stores 380 million acre feet, has availability that far exceeds the Gulf Coast and Carrizo-Wilcox, which store 4 and 5 billion acre feet of water. Well, what's going on there? Does this suggest maybe that there's some overlying reason why availability from the Gulf Coast and Carrizo-Wilcox is more limited than the Ogallala? And I think so. I think we'll see why that is. So how will we approach addressing groundwater recoverability? Well, we use a term that we like to call maximum economically recoverable storage, or MERS for short. MERS is essentially a numerical simulation, which is essentially a compilation of the equations that we see in the paper, and we'll walk through a few of those key ones here today. MERS has essentially two constraints to it. It has physical constraints and economic constraints. So let's talk about the physical constraints first. Well, this might seem crazy to say, but aquifers are not bottomless. That might sound self-evident, but it is surprising to me the number of publications I see in the literature, particularly in the economic sphere, which simply assume a bottomless aquifer of infinite areal extent. I mean, that makes the math a little easier, but it's not very realistic. Because aquifers are not bottomless, an aquifer in a well has a limited capacity to meet demand. And here in the paper, the key equation that we use, the key term that we use to describe that relationship is specific capacity. Now, I put the equations up here for the mathophiles like myself who like to see those kinds of things. And I don't want you to get too lost in it, but I want you to take two key things away from it. Number one, you could do this calculation with just a calculator and a piece of paper. It's not too complicated. And number two, I want to draw your attention to these T terms that I've highlighted in orange. This is T for transmissivity. And what's important about transmissivity is that it actually declines with a falling water level, and therefore means that specific capacity declines as water levels fall, specifically in the unconfined setting. So specific capacity is a really commonly reported term, and in one form where it's converted to, say, a flow rate per foot of drawdown, it's pretty easy to understand. So for example, if you see a specific capacity of 10 gallons per minute per foot of drawdown, then if you draw the aquifer down by 10 feet, then you're producing 100 gallons per minute. Pretty straightforward, pretty easy to understand. The second part of this, to understand how the capacity of the well and the aquifer are able to meet demand, is a maximum pumping rate. And here in the paper, we basically multiply that gallon per minute per foot of drawdown times the available head, right? The available depth to water, right? And so that, for simplicity's sake, is given as the difference between the depth to water and the top of the well screen. And we kind of see that here pictured on the right. We limit the available drawdown to the top of the well screen, because if you go any further than that, then you introduce air into the system, which drastically reduces efficiency and may actually damage the well. So with all of these considerations together, we can kind of partition the aquifer storage into three areas, going from bottom to top. First, we have essentially a dead pool, right, which is the screened interval of the well. Then above that, we have the pumping range. So that's the saturated thickness that needs to be reserved in order to support that drawdown under pumping, that cone of depression. And what's important about the pumping range is it's variable with your pumping rate. Obviously, a higher pumping rate is going to create a larger cone of depression under pumping and therefore require a larger pumping range. And the bigger the pumping range, the smaller the production range, and vice versa. If you have a smaller pumping rate, smaller cone of depression, then it's a smaller pumping range and a larger production range. So ultimately, the limit applied to our model of where the aquifer well can meet demand is the depth to water at which the maximum pumping rate equals the demanded pumping rate. So now let's look at the economic constraints. Effectively, costs increase with depth. in all settings and all conditions. So here in the paper, we discuss pumping costs as equivalent to lifting costs. And we've got a couple of, again, pretty simple equations where we can convert lifting distance to horsepower using a conversion constant. And then we can take that horsepower and convert it to a recoverability, which again is dollars per volume cost, right? To do that, you simply take the horsepower of your lift divided by your wire to water well efficiency, multiplied by a conversion constant times your local power cost. And we use a power cost in electricity. It's probably a little bit low actually, but we estimated it, 7 cents per kilowatt hour. So once we have recoverability in terms of dollars per volume cost, then we can convert agricultural value of crops distributed over the irrigation demand to feed those crops to come up with a dollar per volume cost. With a dollar per volume, dollar per volume value. Once we have a dollar per volume cost and a dollar per volume value, we can simply compare those two to create a simple profit function. So here in the MERS model, the limit we apply is where profit equals 0. Now that's not a very economically efficient or necessarily desirable limit, but it is rational, right? If you were to reduce water levels beyond this point, you would effectively be losing money on the pumping costs. So now let's look at the results of this numerical simulation and talk about what it tells us. First, let's look at those physical constraints. Here, what we see in this curving blue line is that maximum pumping rate we were talking about. Now, this is, again, imagining that whatever the water level, the depth to water might be, you pump the aquifer to the point that the cone of depression under pumping goes all the way to the top of the well screen. So I don't want you to get too concerned about the pumping rates that are very high to the left of this graph, because those might be unrealistic in light of considerations like well screen entrance velocity, upflow velocity, and well screen diameter. Here on the left of the chart, we see a solid green line, and that's just a reference point to show the most exhaustive desired future condition that we found within the central Carrizo-Wilcox study area. It's a change in depth to water of 65 feet. So that's 65 feet of drawdown over 50 years. Here in the red line, what we see is that demand capacity constraint that we call H max. That's the depth of water at which, if the water level is lowered any further than that, the well and aquifer can no longer meet the demanded pumping rate. And so you can see down there along the x-axis, that's a change in depth to water, right? From 0 at land surface to 350 feet, which is kind of a nice average saturated thickness for the Carrizo-Wilcox in the central section. And then of course the black line there indicating the top of the well screen. Now, recall what we said a minute ago about the pumping range and how the pumping range is greatly affected by the pumping rate. That's what this graph here to the right is showing. In our paper, we derived demand from irrigation demand, right? So we simulated a range of irrigation demand from 1 inch per acre all the way down to 1/4 of an inch per acre. So the lower and that's for a 100-acre plot. So the lower your irrigation demand, obviously the lower your pumping rate. And as we said, the lower your pumping rate, the smaller your pumping range. And that's exactly what we see here. The very high irrigation demand pumping rate of 1 inch per acre in this solid red line can only achieve a maximum depth to water of about 150 feet. On the contrary, a much smaller pumping rate, irrigation demand of 1/4 of an inch per acre with a much smaller pumping rate can achieve over 250 feet depth to water before it hits that demand capacity constraint. Now let's look at some of the sort of integrated economic and demand capacity constraints. This is sort of the ultimate MERS, maximum economically recoverable storage results. First, let's look at the unconfined setting. The diagonal blue line that you see there is the profit function. So that's, again, your dollar per volume, dollar per volume value, right, minus your dollar per volume costs. And the harvest value that we use to calculate that value in this example is $154.51. Now that's just a reference number, right? What that number is out there, but I should be back. Sorry about that. So that's just a reference value. It's just showing what the harvest value in dollars per acre per year would have to be to achieve a profit at zero at the very bottom of the aquifer, which here is in the unconfined setting, 350 feet. So again, we see the green line reference for DFCs, and then the red line there is the H max, right? The point at which the aquifer can no longer meet the given demand. And what's interesting about this is that we see that the profit at the H max has declined to $13.36 per acre foot. So it's declined by about 40% of the initial value. So now let's look at the confined setting. The same demand capacity constraints, that red line, still appears in the confined setting, but it's at a much greater depth, right, within the saturated thickness of the aquifer. Here in the confined setting, you can see we added a black dash line to indicate the top of the aquifer. But again, if you look at the x-axis here, you see that the change in depth in the confined setting is much more significant. The maximum depth in the unconfined setting simulated here, 350 feet versus 2,000 feet in the confined setting. So what does that mean? Well, importantly, that means that the change in economics and costs and the profit function are much greater. That reference harvest value to get to the bottom of the aquifer at profit equals zero has gone from $154 per acre per year to $882 per acre per year. A big change. And again, what's interesting here is that while we still see the demand capacity constraint occurring, it's at so much of a greater depth that the change in profit has declined all the way down to 1.51% of what it initially was. So what does this mean? Well, this is sort of interesting. I told you before that those two lines, profit functions, were sort of reference values, and we still see those here. The light blue line down at the bottom left corner is that reference harvest value getting to zero value at 350 feet, the bottom of the aquifer in the unconfined setting, and the dark blue line is the same reference harvest value for the confined setting. But now we've added in a few reference harvest values for alfalfa, onions, tomatoes, and grains. And first thing I need to say is these are, very much reference values. And actually, we believe they're probably overestimations of the actual harvest value, because to be most precise, what we really want to do is we would want to consider the harvest value net of all costs unrelated to pumping. So net of things like, farm equipment, labor, fertilizer, things like that. And these numbers don't really capture that. It's sort of our hope that certainly irrigators who could be applying this model, and perhaps groundwater managers applying this model, might have better estimates for their local condition harvest values for various crops. But even so, even as an overestimation, they tell an interesting story. If you look here at the dark orange line, this is a $440 per acre per year harvest value for alfalfa. And what this shows is that profit goes to zero for alfalfa far before the aquifer transitions to an unconfined setting. So what that means is that this producer is economically limited to pumping from the aquifer in the confined pressurized storage setting. So on the contrary, if you look at something like grains or tomatoes, the value there is far more than sufficient to allow pumping be up to the demand capacity constraint there in the red line. And why is that important? Well, essentially what that might mean, if you recall the storage and yield calculations that we talked about earlier, if you're limited to producing only from the confined setting and the pressurized storage, that storage coefficient is so much smaller that effectively your recoverable yields are orders of magnitude smaller than what they are for someone who can afford to pump from the unconfined setting before they reach their economic limits. So now, before we sort of wrap up and give you our closing thoughts, I wanted to take a few minutes to share with you the sort of our latest efforts and where we're going from here. First and foremost, we're really excited about the prospect of being able to run a recoverability analysis for major aquifers throughout the state, subject to sufficient data availability from notably the Texas Water Development Board groundwater availability models. And we're really excited about this. We're looking forward to being able to run a recoverability analysis for either a hypothetical well, what would it look like if I had a well here, or for existing well infrastructure. I do have a well here. What does recoverability look like for me? An important change that we're making is we're moving away from specific capacity, which is widely reported and easy to understand and calculate, to potentially, more precise analytical drawdown solutions. This allows us to do a few things. We can account for things like artesian flow, where water depth to water is well above the land surface and how that impacts your pumping rate. It allows us to look at partial well penetration impacts, which we'll talk more about here in just a second. We can also, when we put all this together, we can do interesting things like optimize the well screen interval, and we can consider those pesky upflow and well entry velocity constraints. This paper here published with the Water Journal so far did not incorporate any kind of fixed costs, but we're looking at adding those in right now. Drilling costs, for example, could be very significant and maybe even constraining when you're looking at drilling to the bottom of a, say, 2,000-foot aquifer. Similarly, pump equipment costs. In the paper we have published here, we simply assume that you have a pump capable of providing the horsepower required to lift your pumping rate from any depth to water. But again, that can be quite significant. And finally, the paper we published here looks only at agricultural users, which we understand to be relatively sensitive to groundwater recoverability changes. But we also think that domestic groundwater users may also be relatively sensitive. Now, domestic groundwater users don't have a traditional quote unquote value associated with the water they're using, right? And not like an irrigated crop, which has a market price. So some of your traditional economic models break down a little bit, but what we can do with domestic groundwater users is we can apply affordability thresholds. And the EPA has actually generated one of those for us. And they say that essentially water affordability is where the cost is equivalent to about 2% of income. So let's look at those analytical drawdown solutions just real quick. Again, I put the equations up for the folks who like to see them, but I don't want you to get too lost in them. I want you to take away just a couple of important things, right? First, again, we see that orange T, right? And so that orange T, again, declines where the depth to water is declining in a unconfined setting. So that here, we're looking at S, drawdown. And where T declines here, S increases. So the lower your transmissivity, the greater your drawdown under pumping. The second thing I want to talk about with these equations is, obviously these are a bit more complex. You really probably wouldn't want to try to do them with a piece of paper and a calculator. So we need to effectively solve these with computing power. And we've got two solutions listed here. First, there's TICE and then Hantouche. TICE is the analytical drawdown solution used for a fully penetrating well. Hantouche is for partial penetration, and that's really important for a couple of reasons. Number one, you see down here on the bottom left, there can and often is a really big difference between partial penetration drawdown and full penetration drawdown. Here in this example, you see that the total partial penetration drawdown is over 3 times the corresponding full penetration drawdown. And what does that mean? Well, imagine here on the right, you see this sort of bars, right, indicating the well screen. Well, full penetration would indicate that the entire saturated thickness of that aquifer is screened by the well. Now, that might be the case in a confined setting, but it certainly won't be the case in an unconfined setting. Again, some of the saturated thickness needs to be reserved to support pumping under drawdown, and of course, the relevant production range over time. But what we see is when we run these solutions, we see that there is a large impact to the pumping, the drawdown under pumping based on the screen interval. The smaller the well screen, the larger the pump drawdown under pumping will be. So again, recalling one of our objectives here in the latest and greatest version of these solutions is to optimize that difference, right? We obviously want to reduce the drawdown under pumping as much as possible because that's equating to lift and therefore cost. But we're also want to maximize the production range, right? And minimize that well screened dead pool. So that's something we're working on right now. I'm very excited about. Next, we're looking at, as I said, we want to run this analysis for major aquifer footprints throughout the state. So here what I have is some representations of the central Carrizo Wilcox. On the left, what you see is essentially the grid squares for the model. And these are showing a 1 square mile area, which is pretty standard for most of the groundwater availability models. Some of them have a little bit smaller squares in certain areas of interest. As you can see, with something as big as just one section of the Carrizo Wilcox, that comes out to about 22,000 cells. And so given that we're running, a complex numerical model with partial differential equations and optimization solutions, now we're talking about the necessitating high performance computing, which fortunately we have access to. So what we can do is, as I said, we can pull the data points that we need for our equations and solutions out generally from the groundwater availability models and some other sources. So for example, here on the right, we have digital elevation. What does the land surface elevation look like? Here, this is processed from the National Elevation Dataset 2013 to a 1 square mile basis. And importantly, so what's this little purple dot? We're starting with the Carrizo Wilcox central section for a number of reasons, including the fact that the model is fairly new and robust, but also, it has potentially far-reaching impacts. This little purple dot is the approximate location of the well field for the Vista Ridge pipeline project, which delivers water to users in San Antonio. So what happens in the Carrizo Wilcox, the impacts there too are not simply limited to the folks who live over the central Carrizo Wilcox. Other data points we need, right? The saturated thickness here on the left of the aquifer, but essentially derived from the depth of the top of the aquifer and the depth of the bottom of the aquifer. And then, of course, you need the depth to water, which is shown here for 2010 levels. In the dark sort of reds and oranges, you have artesian conditions, right, where the depth to water is above the land surface. And then sort of in the darker green areas, like over here, we have this little circle indicating a lot of pumping over time. We have a depth to water, which is no longer artesian and falls below the land surface. And finally, what we can do with that is we can kind of put our recoverability results together with other data sets to say really valuable and interesting things, right? As I mentioned, we're interested in looking at domestic groundwater recoverability. And the threshold for that is set by the EPA as 2% of income. Well, we have income data in the form of American Community Survey data from the US Census Bureau on a census tract basis. So what we will be able to do is we'll be able to compare our groundwater recoverability within a certain area to the income within that area to make estimates of where groundwater availability is or is, or excuse me, recoverability is or is not affordable to certain user groups. Similarly, with the agricultural users, we can compare our groundwater recoverability results with existing or potential agricultural uses. So here on the right, I have pictured the cropland data layer from the USDA National Agricultural Statistical Service 2019. And you can kind of see exactly where we're looking at various crop types. So what can we take away from this study? We wrap this up. First, groundwater availability. There is no universal solution throughout the state. We currently manage using these desired future conditions, which are a nexus of many potentially conflicting groundwater management objectives. Everything from subsidence to environmental flows to socioeconomic impacts to hydrological conditions and interests and rights in private property. Total estimated recoverable storage. It is currently the state's best estimate of groundwater recoverability, but its limits are arbitrary. There is no consideration for pumping dynamics nor the economic feasibility of withdrawing the water. And importantly, it may drastically overestimate in deep and confined settings. Our preliminary results indicate that for high pumping rates, comparatively high pumping rates, such as in agricultural usage, in an unconfined setting, the 25% metric may be about right in terms of recoverability when you account for that well screened dead pool and then the drawdown under pumping, that pumping range. For a much smaller pumping rate, such as a domestic user, it could be quite a bit higher. However, in deep and confined settings, again, if the economic constraints kick in and don't allow the user to access water from the very deep, unconfined part of the aquifer, then essentially the amount of water that can be produced is very, very small. Again, you're considering those storage coefficients and the orders of magnitude and difference between them. So in those settings, in those conditions, the volume of water that could be recoverable for that user could be as little as 1% or less of what TERS would estimate. So here we apply this numerical model for maximum economically recoverable storage to address groundwater recoverability. As we said, it's a key element of groundwater availability. And importantly, it was deliberately designed to be directly compatible with depth to water based desired future conditions. We're evaluating changes in recoverability with changes in depth to water. And that, again, is the most commonly used metric for managing groundwater throughout the state. We scientifically quantify changes in recoverability using two key parameters: physical limitations, which are ultimately constrained by the aquifer and well capacity to meet demand, and then economic limitations, right? Again, costs increase with depth to water in all cases. It's ultimately here constrained by value and willingness to pay. If you're a domestic user, willingness to pay, by the point where you get zero profit. If you pump any deeper than that, you're losing money. We do want to reiterate that that's a rational limit, but it's certainly economically inefficient. And all users are economically incentivized in all cases to minimize changes in pumping costs and effectively changes in profit. And the last key thing that I want to mention is that one size does not fit all, right? Our results are highly subjective to use. If you are a alfalfa farmer, right, your recoverability is very different from a tomato farmer. And similarly, a tomato farmer's recoverability might be very, very different from a microchip manufacturer. So one size does not fit all. But these tools do allow us to quantify changes in recoverability for known uses and conditions. And this could be really valuable information, understanding how groundwater recoverability changes in either a physical or economic sense with either planned or potential changes in depth to water could be extremely valuable to groundwater users, managers, and even policymakers. So finally, I just want to do a few acknowledgments to the folks who have kindly supported this research. We've got the State of Texas Advanced Oil and Gas Resource Recovery, or STAR program, the Planet Texas 2050 UT Grand Challenge, of course, the Bureau of Economic Geology, the Bureau of Economic Geology Excellence Fund for research and for water research and policy, and then most recently, the Texas Water Resources Institute. And so with that, I'd like to say thank you all so much for attending. I know the webinar was not free, but we really appreciate that. And the funds are going to the Water Journal nonprofit. And so with that, I am happy to answer any questions you might have.
Justin, this is Todd. Great job, by the way. So Michael Young and Charlie Kreitler will be joining Justin here in the Q&A period. And the first question, Justin, we have comes from Robin Geary. And just note, you can actually, if you want, you can also submit questions anonymously. And Robin's question is, have you looked into domestic groundwater wells average depth, and at what point in your analysis would they have to deepen a well?
That's
and
a really
she goes on to make a point before I finish. She says domestic user impact of economic recoverability would likely influence property value?
Right. Now, it's a really interesting question. That we're in the thick of those considerations right now, right? And what's really interesting about this is a few things, right? There's an interesting balance going on. Domestic groundwater users have, first of all, a much lower pumping rate than, say, an agricultural user. So what that means is the lifting costs of pumping are probably much smaller, right, than they are for an agricultural user with a very big pumping rate. Um, so then that kind of lends one to think that the economic considerations that are going to be most relevant to a domestic user are going to be, for example, some of those fixed costs, right, like drilling costs. And indeed, what we see is that domestic groundwater users very commonly do not drill all the way to the bottom of an aquifer. They will drill to essentially a point within the aquifer that their drawdown under pumping, won't interfere with the well screen, and will give them a little bit of wiggle room in terms of production over time. And so the questions that we're looking at right now are, well, what's the balance there, right? How do you minimize those drilling costs, right, against your long-term recoverability? And it's a really interesting question. We're also looking at uh, how to add to the model considerations for dropping the well, right? Which is, honestly a pretty easy thing to do if we have a user given drilling cost rate. So if you say, oh, well, it's about $25 per foot of drilling and screen installation, then we can basically program the model to say, all right, well, at the point where depth to water reaches a demand capacity constraint, well, then we can add in additional fixed costs for dropping that well further. I hope that answers the question fairly well. Essentially, it's very interesting. There's a lot of optimization trade-offs that we're looking at right now.
So I'm going to assume that if Michael or Charlie want to weigh in, that they'll unmute and do that. Michael, you going to weigh in on that?
No, I mean, I think he answered the question pretty well. I'm trying to mute myself when I'm not talking because there's a thunderstorm right outside. I'm just trying to keep the audio clean. But no, I think that he answered Robin's question pretty well.
So we now have a question from Charlie. You say something?
Yeah, and Robin, Charlie Kreidler here. It's a very relevant question for Barton Springs, and particularly in the Trinity, where so many of the domestic users in the Trinity drill a well till they hit the top of the water table, and that's enough, rather than going down and getting a complete section. So it's a very real issue for the domestic user.
Yeah, and actually, just another thought on that. Remember we talked about partial penetration effects, right? So another part of that kind of quandary is, well, if you're only drilling to a very limited degree within the saturated thickness and screening kind of a minimum amount of that saturated thickness, again, recall that your drawdown under pumping is going to be much greater, right? Because of those partial penetration impacts. May not be enormous with a really small pumping rate, but it's another piece of that optimization puzzle.
So our next question is from John Dubnik, and John asks, have you considered applying this analysis to more realistic use cases? For example, irrigated agriculture demands in the unconfined Ogallala, or municipal demands and long distance export over the Carrizo Wilcox?
Yes. So as I mentioned, what we're working on right now is applying this, the latest and greatest version of this numerical, model to as many of the major aquifers as we have sufficient data for, right? And what we're hoping to do with that is essentially, use the data that we can get from the Texas Water Development Board groundwater availability models on that 1 square mile basis to estimate groundwater recoverability for either a hypothetical or an existing well throughout that entire aquifer footprint. And actually, I think that when we do that for the Ogallala, it will, really just serve to highlight this difference in recoverability for very deep and confined systems versus shallow systems. Because I suspect that what we'll see is that overall recoverability in a shallow, unconfined system like the Ogallala is far greater than what we see in the deep confined Carrizo Wilcox, and that's essentially the sort of reason why we see this, universal discrepancy in availability between those two aquifers in the state water plan. Um, Municipal pumpers are, another user group that we're looking at right now. The underlying model is effectively the same, right? The only tricky part gets into sort of the economic constraints and um, how you apply the value that the municipality is getting from its user fees to that volume of water pumped, right, to come up with that dollar per volume estimate. But we're looking at it right now. Yeah, essentially, we're hoping to apply this to as many real world useful examples as possible. Thank you for the question, John.
So Charlie, it looks like you're unmuted. Are you going to weigh in? Or
He's
nope,
muted
now
now.
you're
he's
muted.
muted.
Okay.
I will properly mute myself in case of the thunderstorm that's in North Austin comes to South Austin.
No, and I think
Michael?
I'll just weigh in really quickly. Justin put that little dot on the map for the source of water for Vista Ridge. So we are trying to account for some of these some of those water uses, but the goal here is to keep the tool flexible enough so that it can be used to answer a wide variety of realistic use case and scenarios that we haven't really thought about yet. And I'm not sure if Justin had mentioned that one of the things we're doing now is we're trying to enable this so that it's a completely web-based tool, so that anybody would be able to go to a website and be able to plug in the well characteristics, well construction, aquifer characteristics, and then run the model independently, so that it's not a tool that you have to email and you don't have to know Python coding in order to make it work. And so we're investigating doing that now. We hope to have a beta version up reasonably soon. So that way, whether you're looking at interbasin transfer, whether you're looking at groundwater surface water interaction, or whatever the case happens to be, that anybody would be able to use it.
Right. I did not mention that, and that's a great point. And what we're really excited, what I'm personally really excited about that is, first of all, like Dr. Young said, it it puts all the business logic in the background. You don't have to know Python. All you have to know is what are your local conditions that you're interested in. What's the depth of my aquifer where I live, or the place that I'm looking at, right? And importantly, what's really cool about it, like I said, is we can look at either hypothetical infrastructure or existing infrastructure. So if you want to run this web-based platform to see, well, how does groundwater recoverability change for me and my well with depth to water, you can go in and plug in all of your relevant well characteristics. Or if you're interested in, well, what does groundwater look like here hypothetically, right? Recoverability look like here hypothetically. You can allow the model to just sort of optimize everything for you, right? But what should the well screen be if you're interested in minimizing your economic impacts, or what should it look like if you're interested in maximizing the yield overall time, right? And I think that's really going to be hopefully a valuable tool.
So Justin, let's move to the next question, which comes from Tyler Thompson. And so this has got two parts to it. He's asking about the decline in availability as a result of population increase. And he asks, is the rise in population stratified by what types of consumers that population represents in terms of agriculture versus domestic users, I think. And then there's a second part which says, if it does, would increasing water reclamation infrastructure to correspond with increased domestic users have a positive impact on the goal of increasing the ability to preserve more groundwater by using less?
Yeah, absolutely. So let's take both of those parts of that question in turn, right? So the first question about, well, 70% increase in population projected by the state water plan, what does that population growth look like, right? It's an interesting question, actually. For quite a few years now, what we've seen in demographics in the state of Texas is a shift from urban to rural to urban, excuse me, folks moving to the cities. And so the state water plan, which if you haven't read, I very strongly recommend. It's a very interesting read. You can learn quite a lot. The state water plan still, as I understand it, projects that most of the 70% increase in population will be to the urban centers, right? So the increase in demand for water that we would see throughout the state is, by and large, municipal demand, right? Municipalities pumping to serve those thirsty city dwellers. There's some sort of so things like agriculture and other uses, right? Rural uses are not anticipated to increase nearly at the rate that urban water use is expected to increase. But it's interesting. Obviously that plan was written pre-COVID, and now there's sort of a growing discussion out there about, well, how does the COVID virus and sort of the shift in some workforces for people working remotely, how could that impact some of these population projections? Could we see greater populations moving to sort of more rural or peri-rural kind of locations, and how might that impact the projected demand for those locations? So yeah, it's really interesting stuff. It's mostly domestic. And then again, so to answer the second part of the question, again, the state water plan looks at these kinds of things in great detail, right? We talk about the deficits that are projected, and the state water plan has whole sections talking about the solutions that are currently being implemented to sort of meet water demand. And one of the big stars, if you will, of those plans is things like recycling, right, and reuse of water and things like that. It's projected in a lot of planning groups to conserve quite a bit of water. And of course, if you're conserving water or essentially meeting some part of your water demand from some other source like reclaimed wastewater or something like that, then that's going to alleviate demand on your other water sources like surface water or groundwater.
So Justin, let's go to the next question, which comes from Patrick Schreiber. And Patrick is asking about the state's Creso-Wilcox aquifer model. And it's a robust model. And he's asking, can you talk about the link between the quality of groundwater modeling and the tool that you're developing, the new tool?
Yeah, for sure. As I did say that the sort of the robustness, if you will, and the quality, if I can use those terms, for the central Carrizo-Wilcox model, central that is one of the reasons that we were looking at that as kind of a developmental test case. The other big reason, obviously, is the massive amount of storage in the Carrizo-Wilcox, and trying to evaluate the story there, the difference between storage and availability, and trying to tease out the recoverability causes of that. The linkages are pretty straightforward, right? To run this numerical simulation well, you need to have a good estimates for things like your aquifer parameters, right? What is the hydraulic conductivity, for example, of the aquifer, right? And hydraulic conductivity as being a parameter that estimates how easily or difficult it is to flow water through the aquifer. Well, that's a really key parameter that goes into describing things like your the pumping impacts, right? Pumping dynamics, right? Your drawdown under pumping and things like that. And so when we're running this model, for example, if we're running it on a hypothetical basis for an entire aquifer footprint, then the quality of the results in terms of recoverability modeling are going to be directly related to the quality of the inputs that goes into it, right? If there's a lot of error and uncertainty for any one given square mile regarding things like hydraulic conductivity, then that error and uncertainty is going to get promulgated into the recoverability results. So that's it's a pretty direct linkage, right? And you know, on the only other thing I would say about that is, you know, the newer the model, the easier it is for me personally to work with it, right? So the Carrizo-Wilcox, for example, has the central Carrizo-Wilcox groundwater availability model has a pretty comprehensive geodatabase files, right? Whereas I think a lot of us know that our some of our groundwater availability models are getting on in age, and you know they require, you know, a little bit of a different skill set to access that data. But I gathered that some of those are being updated sort of as we speak. So that's good news.
Yeah, and I just wanted to add one point to that, and that is that the models that are used for the GAMs, these are much more complex types of models than we're using here. Those are all kind of linked, discretized models, you know, of using mod flow across much larger areas. What we're doing is we're only looking at a point data and then solving an analytical equation for a point scale. And when we start looking at uncertainty, what we can do is we can run the model very quickly, say 100 times, with a range of property values that would account for the things we don't know: the storage coefficient, the aquifer thickness to some extent, hydraulic conductivity, and so on. And then from there, we can come up with a range of outputs to sort of bracket the possible drawdowns or the costs, for example, of pumping the water based on the things we aren't sure of. And it does a couple of things. Number one is it sort of provides it helps us to understand, first of all, the sensitivity of particular areas to particular properties. It helps us to understand where we need more data. If we are under parameterized, if we don't have a whole lot of data in certain areas, and we know there's a lot of error and dependency, we can go in and say that these are areas where we need more information. So the models that are used in the GAMs and what we're using, we're all using the same data, but if different analytical approaches to solving more or less the same question.
Mm-hmm. Mm-hmm. That's an excellent point, right? About, yeah, agreed completely.
So Justin, let's go to Carolyn Layfield's question. She's asking about how you're able to determine these costs, and the costs, how they differ from region to region. She's, you know, asking, is that related to the cost of, you know, drilling through different types of materials to reach, you know, groundwater?
Yeah, no, that's an excellent question. So let's look at costs in two parts, right? First, there's lifting costs, right? And that's what's explicitly considered in the paper, right? Everything else is, you know, for example, the fixed costs and drilling costs. Those are elements of the model that we're incorporating right now. The lifting costs are actually pretty straightforward. Gravity is consistent, right? So there's a certain energy requirement of lifting your pumping rate over a certain distance. The only really tricky parts about that are determining what that distance should be, right? In the paper version of the model, we simply assume that the lifting distance is that current depth to water, right? But using the analytical drawdown solutions, we're actually able to describe what the lifting distance is on a minute by minute basis, right? And so that's actually, you know, nice and a bit more precise. It actually reduces the lifting cost slightly because, as most of us know, That drawdown curve does not happen instantaneously. At first, in the early stages of pumping, that the drawdown is rather small. So the total lifting distance at the beginning of a pumping session is smaller than the total lifting distance at the end of a pumping session. So that's lifting cost. Again, pretty straightforward. Gravity is constant, right? And we saw that in those equations. They're pretty easy to calculate yourself with a piece of paper and a pen. The fixed costs are a little more complex, right? And so this is where, so let's look at drilling costs, for example. To estimate drilling costs, I actually wound up surveying water drillers sort of across the state and just kind of asking them, well, what is your drilling cost on a per foot basis? And that's the kind of standard is it's given to consumers on a per foot basis. What does your drilling cost look like? And one of the things we find that's interesting is that varies with not so much, the aquifer types and the kinds of rock you're drilling through, maybe a bit, right, from region to region. But the number one thing that drives changes in pumping costs is well diameter. And well, that's interesting. Well diameter is directly related to your demanded pumping rate. So if you have a very high demanded pumping rate, you're going to necessitate a very large well diameter, which is going to necessitate a very high, comparatively speaking, drilling costs. So to sort of Michael's point about the range of parameters that we might see and how and sort of the range of recoverability that we might see. The current version of the model that we're building that considers all these fixed costs will let you the user choose some of these things. If you are, for example, have an existing well and you say, I know I drilled this well last year and it cost me $30 per foot of drilling and I drilled it 100 feet down, then you just put that right into the model and it'll calculate accordingly. Alternatively, if you're interested in a hypothetical well, what if I had a well here? What would groundwater recoverability look like? Well, then the model accounts for that and allows you to set an estimated range of what your drilling costs might be, but then it'll kind of go through and check that against your demanded pumping rate and the sort of calculated well screen diameter that you would need to support that demand. And that's where those well entry velocity and upflow velocity limits come in, right? You can't really have a well diameter that's too small, right? Or some of those limits will be breached. So it can kind of calculate that for you.
And the only other thing I would add to that is that we put in the electrical costs in terms of number of cents per kilowatt hour, for example. And so once the water level drops down, the well has to work harder to push the water up, and we have that power curve in the model. So that as the water level goes down, we're able to calculate what the additional electricity costs are going to be to run the pump.
Right.
So to Carolyn's question, that can be calculated automatically by knowing what the cost of electricity is and whether, for example, if you're completely off the grid and you're running your own say solar system with a battery, well then you're able to reduce those down to near zero. But if you're on municipal or if you're on the grid and the grid's going to cost you 12 cents a kilowatt hour, for example, you can just plug that directly in and have it calculated for you.
Right, exactly.
So here is a comment from John Dupnick, and John tells us that just recently an update to the Central Creso GAM has been published that incorporates data collected from the Vista Ridge project.
Aha. I'd seen some news out of the GCD there about how the GAM was performing with respect to that pumping going on there. So that's good to know. That's interesting. Very interesting.
So the last two questions, it looks like, well, really one question. Tyler says that Justin, I think he just answered it while he was typing his question. And so we'll just see if anybody has any other final questions they want to ask. And while we're waiting on that here a minute, any other comments, Justin, do you want to make, or Michael or Charlie?
I'll defer to Michael and Charlie since I've done most of the talking here.
No, I'm good. It's 11:15, and so if there's other questions, we're happy to answer. And I think Justin put his contact information. We're really, the thing that we really would like to know from folks here is how would they see a tool like this being used and being useful. There's a lot of things that we could add to it. We just want to try to add things that are relevant.
Yeah, in terms of contact, I actually forgot to slap my email on this last slide. Apologies for that. But if you go to the journal website and find the paper that we published, I am the contact author there. So you can pull up an email for me with just a click of a button, and I'd be happy to answer any questions you might have or listen to your thoughts about, how this could be useful or how it could be improved. Happy to send you copies of these slides, anything like that. Be happy to do.
Okay, Charlie here.
Oh, go ahead, Charlie.
Just read the paper. It's a very complex, very interesting process that Justin has come up with. And it will take a while to read through and fully understand everything that has been done there. The webinar is very interesting, but it opens the door for you all to look at it more carefully and understand what has been done, because I think it's a significant contribution.
So we did get another question. And so this question has to do with subsidence and faulting when drilling increases. And so the question is, how much weight is given to those types of things? Says, when we talk about property owners and their drilling costs and profits, but the changing weather patterns, hurricanes, floods, et cetera, are these kinds of things considered in the analysis?
Well, that's an interesting question, right? So first, let me go with the easy part of this question, right? Well, how much weight is given for subsidence? Well, in this model, none. And there's a very simple and good reason for that, right? Remember those desired future conditions considerations, right? And they list all these things that groundwater managers are required by law to think about when managing their groundwater resources. As I said, some of those things can be directly conflicting, right? So for example, you might have a lot of people that want or need groundwater, but if they pump it, it will, create a bunch of subsidence and houses might sink, right? So how do you manage that balance, right? That is a local control question, right? Of how those groundwater managers assess all those conditions. What we're really trying to do here is just address one piece of that pie. Right, we're trying to address the recoverability element of it, right? As for human use, right? And that, again, that's just limited by physical constraints, demand capacity constraints, and economic impacts, right? All the other pieces of the pie have to be taken together, but we are trying to improve this part of it. So I hope that makes sense. And then talk about private drilling costs and profits. Yeah, I mean, like I said, we're incorporating those fixed costs like drilling costs into the model right now. Actually, it's pretty much done. We're just sort of making final tweaks. Changing weather patterns. Well, so that's sort of an interesting, what I would say is a driver for why we want to know some of these things, right? What happens if we have another drought of record, right? Or what happens if we have a drought that exceeds the drought of record? Well, you could see where it might be incredibly important for groundwater managers at that time to understand how changes in water levels, which could be changing rapidly under a drought of record condition, will impact various users and wells. So that's kind of like a context driver for, why we might need this kind of information. One reason, anyway.
All right. Well, I think we've reached the end of questions. And so let me just say, Justin, thank you so much for your presentation and for the Q&A. And Michael and Charlie, thank you for lending a hand here on the Q&A. I thought that was very interesting.
My pleasure. Thank you for having us.
And thanks
All
for
right.
everybody for being here and for helping to support Texas Water Journal.
Agreed.
Ditto. Yeah, I wish I'd thought of that. Saying that. So, anyway, we're probably a month, maybe a little less, until our next webinar. And so when we get that scheduled, everybody should receive an email about that. And just to tease a little bit here before I go, the journal will be publishing a new paper on Monday, which is not about groundwater. So, but I think it's going to be very interesting nonetheless. Anyway, thanks again. And thank you to everybody who has called in and participated today. And, we appreciate you.
Here. Thank you so much, everybody.
Thank you. Take care, everybody.
Bye-bye.